Back to the lab.
I'm just gonna drop that report for you. Yeah. And how do we get the most optimal response? Is essentially by the coefficient you're gonna use here. The coefficient for the time one, the time related one is the dt, which is the time derivative. We have a kc and kp, right? The coefficients that we have here are the nomenclature here is different. They use a different one. So we have kc, tl, and td, right? And two coefficients you play with them, and the response you're gonna get is gonna be different. Like one response may be an unstable system, which gives you a huge peak. You wanna minimize this peak, that's your goal, and then you wanna minimize the response time as much as possible, right? But if you get this huge peak, of course you are going to overcompensate, and you get a very huge minimum here as well, and then this may cause instability in your system. So you're going to get an unstable feedback system, right? It will never get to a stable solution for you. So you are essentially, your rate is going to be between an unstable system and the most stable case that you're going to get. How do you get this? You're just playing with the coefficients. I guess you have to come here.
Are we writing the code, or the code's already written?
No, the code is already written. Just have to change the code. So the code is a C code, not the C++, a regular C code. My plan was for you guys to write the code, but we didn't get to that plan. And so this is essentially an executable that we have taken out. We have created using the C. You can set your flow rate here. This is the flow rate that you are reading at any time. At this point, it must be 0. You see the flow rate. And then these are the coefficients you're going to change. Right now, we have the coefficients 1, 0.01, and 0. Okay? Kc, Tl, Td. The red line here shows your set point, right? We have set it to be 30, right? And the yellow line here is the response. But this is just for your visualization. Your data recording is done by this computer, which is a regular. This is something that you have seen here. This is National NI Express, right? We have worked with this a lot this semester. You essentially you run the system. You run this as well. You want to record this. Everything is already set up. You don't need to set up anything. And what this gives you you want to read this white voltage. Okay, this gives you a voltage, doesn't give you a flow rate. The first thing you want to do in your result and discussion part of the lab report that you are supposed to submit is to calibrate this voltage to a flow rate, right? And it's very easy to calibrate. Like for example, it's giving you, how many volts is giving you? 1.7, yeah. Oh, so you care about the red line, sorry. You want to record the left. Let me stop the recording. Okay. You care about this red line, right? And right now we are at 1. That's 1. Okay, none of these is 1.7. That's alright. You can just calibrate either of the voltages. It will give you the response time. Let's do the red one.
Well, this one's going a little bit above 1.8 at some points. I think it's just because you stopped it.
Let's do the red one then. Yeah.
See, like now it's 1.9, now it's 2.
Okay. So you take the voltage that you're reading, you're saving with this system, right? and you know your set point, after it has become stable like this voltage corresponds to your set point, right? Then you change the set point to 20, for example. No, I'm not done yet. Just run. You change the set point to 20, you get another voltage, right? You do it 3 times, you essentially get a linear fit that gives you the correlation between voltage and CFF, right? Does that make sense?
Mm-hmm.
Okay. So that's the correlation part. What do we want to get? Essentially, you make sure you have to, whenever you want to read a new data, you have to stop the recording and redo the recording to avoid having like millions of data points, right? So let's start. You want to start from the set point of 10 and then go up to 30, 10, 20, 30, right? Then you want to try to make this flow 0 as much as possible. Okay? And that is the time you want to record. You see the response here? It went from 0, then huge peak. This is the response, right? This is what you want to show, right? You want to change this response, the response time, the response peak, whatever, with changing these coefficients. Mix and match. We can choose whatever coefficient you want to choose, but you have to compare 5 different coefficients. That's the idea. Okay? Is there any questions so far? Okay. So is this clear? The goal of the lab is to find the most optimum coefficients for your PID, for the PID system, out of 5. So we are not doing any optimization, we are not doing any mathematical calculations, which you can do, but we're just gonna choose 5, random 5, and see which one is gonna give us the most optimum solution. And then you do it for 3 different flow rates. You do it for 10, you do it for 20, you do it for 30. And essentially, you can either put an obstacle here, or you can, every time you can stop the program and then run it to get the initial response. So it goes from 0 to, that will be the initial response. That actually, this is a better idea, but if you're too tired and you don't want to just turn off the program and click again, you can put your hand here. Okay, so it's essentially you have to do this for 15 times. There's 5 of you. Yes, each one of you do this 3 times, right? And the coefficients you want to use, just change these 3 as random, but remember the original ones, you want to set it back to the original ones. And this original one doesn't mean that necessarily these are the most optimal. Because like one of them, we are essentially taking the time derivative out of commission here because it is set as 0, right? So our PID system is just a PI system at this point. Does it make sense? Mm-hmm. Okay. And don't forget to record the data because you want to plot the responses. And eventually, what I really need from you, you have to have an explanation in the result and discussion part and everything. But I also need 3 different plots, right, for these 3 different set points. And you want to have the response on top of each other. So 6 lines, 1 straight line that represents your set point, and then 5 responses for each coefficient, for each set of coefficients. Is there any questions?
What is the time step in the LabVIEW program? Can you make it bigger so that we don't...
You can do whatever you want to do to the program, right? I'm pretty sure you already know how to handle this, right?
Sort of.
Yeah. Actually, steps that's right here. You can change the rate, samples to read. That's your time, right? Okay. If there's no question, thanks for recording, Josh. And yeah.